Okay, students, last part of the lecture that we're going to talk of this first part of the lecture is Maxwell's theorem of equipartition of energy. So earlier on in the lecture, we mentioned that for a single atom, it possesses an average translational kinetic energy of 3/2 kT. Now, where did we get this 3/2 kT from? Well, under this theorem, equipartition theorem, any degree of freedom, we call the degree of freedom F, contains half RT of energy per mole. It'd be half kT per molecule if we change the constant R to K. Alright, so we consider monoatomic gases. So we have derived CV and CP for monoatomic gases, and we said that the kinetic energy possessed by monoatomic gases is 3/2 kT per atom, or 3/2 RT per mole. Right, and how do we get that? We got 3 translational degrees of freedom. This is because for a monoatomic gas, right, what we can have is the monoatomic gas itself translating in the x-axis, in the z-axis, or in the y-axis. And any diagonal motion can be resolved into one of these directions. Therefore, this is 3 independent directions of translation of the center of mass, thereby giving us 3 degrees of freedom. We also can imagine this atom rotating, but since under our assumptions for ideal gases, the gas molecules themselves take up 0 volume, there is no moment of inertia associated with such a rotation, right? So therefore, there is no energy associated with its rotation. Now, if you take a look at the diatomic case, for example, oxygen molecules, which is O bond to O, alright, we can see that in addition to the translational degrees of freedom, there are rotational degrees of freedom. So for the rotational degrees of freedom, we can get an oxygen molecule looking like this, rotating horizontally about this center axis. Right, so this is one axis of rotation. Also, we can have an axis of rotation into the plane like this, represented by the cross. Okay, and then therefore, it is rotating in this vertical axis. Alright, so there's actually 2 degrees of two modes of rotation for the oxygen molecule, and each mode of rotation also gives us half RT of energy per mole, or half kT per molecule. This gives us a total of 5 degrees of freedom for such a diatomic gas. So the more complicated the molecule, or the more polyatomic the molecule is, the more degrees of freedom there will be in rotation, because we can find more axes of rotation, giving us a larger degree of freedom F. So per molecule or per mole, the expression for the kinetic energy at a given temperature will be different, and therefore our derivation of CV and CP will change as a result, but you should be able to derive them yourself getting these values. Alright, so when you're free, do try it yourself, following the same derivation that we did earlier on for CV and CP. Alright, so there are a few examples here which you can look yourself and try yourself. And lastly, we will look at the adiabatic expansion of an ideal gas. So here we have a cylinder of gas again that is insulated, and this gas can be forced to expand by removing some mass on top of this piston, right? Now, since we are insulating it, this process happens quickly and no time for heat transfer with the environment. So as the volume increases, right, the pressure and temperature has to drop. Now, the relationship between pressure and volume during such a process, which is adiabatic, is PV to the power of gamma is constant, where gamma is the ratio of Cp to Cv. Alright, and on a PV diagram, such an adiabatic process will occur along a fixed curve, which is different from the isotherm, but such a fixed curve is called an adiabat. Why is it an adiabat? Because this product PV to the power of gamma must be a constant, so therefore it will produce a fixed curve on a PV diagram. So we can say that if a gas is taken from a state I to a state F, the product PV gamma must be equal to PF gamma. Alright, and then we can write this process in terms of T and V using our ideal gas equation to eliminate P and write this equation. nRT over V times V gamma equal to constant. And you can see that we now have a lot of constants in our equation. So except T, right? So T times V to the power of gamma minus 1 will be constant as well. Okay, just a quick note, we have to talk about free expansions. Although free expansions also is adiabatic, alright, because there's no work done on the also there's no heat exchange with the environment. So for free expansion into a vacuum, it is considered adiabatic. But in this process, right, the expansion process is different from our normal adiabatic process, which is able to follow a curve. Recall that when we're talking about free expansions, it's just the initial state and the final state that is known. So this equation PV to the power of gamma equal constant will not apply to free expansion, even though such an expansion is also considered adiabatic. Alright, so please do take a look at some of these worked examples, and I will proceed on to part 2 of this lecture, which is on entropy.